Thank you all very much for coming today. We are pleased to have Maxime van der Moortel give the first seminar in our online mathematical physics seminar at Rutgers University. Today, he'll be telling us about space-time dynamics in general relativity, old and new. So without further ado, take it away.
Thanks, Larry. It's a great pleasure, of course, to speak in your online mathematical physics seminar. So when I was asked to give this talk, I paused for a second and wondered what I was going to talk about. And I decided rather than focusing on my own work, it was perhaps better to give a sort of review talk of an approach in general relativity, which is sometimes called dynamical general relativity or space-time dynamics. And this has now become sort of one of the major branches in mathematical research in general relativity. And the premise is as follows. The premise is that you fix some data at time equals 0, so some snapshot of space-time. And based on this data, you run the Einstein equation to see the evolution of space-time. And this approach is very successful in addressing questions like how was the universe born? What are the dynamics of stars? How do black hole form? Galaxies and such? All these questions are very dynamical in nature and can be mathematically addressed using this framework. And this has proven tremendously successful, in fact, in mathematical research, with many impressive results in the last decades. And so I thought I would give you a selective history of some of them. So of course, I mean, this goes through my subjectivity. This is by no means a complete or a comprehensive story, you know, of everything that's in dynamical GR. But I think I wanted to give you a few landmarks which I think are important and which sort of shaped the research in this field.
Can I ask you a personal question?
Go ahead, Shelley.
Yeah. What is your opinion, though, about the dynamical approach? Do you think it's merely convenient, or do you think it's sort of that general relativity is fundamentally a dynamical theory?
I think it's fundamentally a dynamical theory. And I think there are a lot, if you sort of restrict yourself to stationary solutions, there are many things that you can't really understand. And this is not clear a priori. Sort of, if you look at relativity and you don't have a lot of knowledge, you could sort of think a priori that, you know, why bother about dynamical things at all? But when you sort of start to know more, and, you know, in particular, this recent result that we have sort of indicate that there is something very fundamental in the dynamics of space-time. And this is too often forgotten, in particular on the physics side of things, where, of course, if you want to simplify, you can think of everything as stationary if you wait long enough. But it's not as simple as that, even on the fundamental level. That's my personal take.
Stationary, you mean what?
Time independent. That's what I mean by stationary.
Yeah, but I mean, what do you regard the four-dimensional point of view? It is stationary from the four-dimensional point of view, in the sense that you're just talking.
Oh, that's what you mean.
And you could take the point of view that as a matter of convenience, we want to slice it and see and get a sense of evolution in terms of a foliation, but that's not fundamental. Or you could say it is fundamental, and sort of time has a more fundamental role, more than you might think it has.
So that's the thing, you raise a very good point. I mean, time itself is not fundamental because it's a theory of space-time, right? So time is not a well-defined notion, and you can sort of introduce time in many different ways that are non-equivalent, but evolution is fundamental, I think. I think that's the point I will want to emphasize, meaning that you can make sense of a geometric evolution, you can make sense of what it means to have Cauchy data and to create a maximal globally hyperbolic solution. That's something that makes sense geometrically. Even though to formulate it in practice, you always need to introduce an artificial notion of time. So time maybe is not as fundamental, but dynamics is. So I think that's quite important to realize. You can sort of make a theory that's purely geometric without having to say this is time. You don't have sort of to slice, even though naively you think that, you know, making some slices and think of a snapshot at time equals 0. This is of course a naive picture, and I'm explaining it like this. But that's another fundamental part. But dynamics, I think, is fundamental and can be expressed in a way that does not depend on the observer, in a way that's completely geometric.
Yeah, we should discuss that, but this isn't the time for it. Okay.
Right, but no, but that's a very good point. That's a very good point. Yeah, thanks. Yeah, we can talk about that at lunch later if you want.
Yeah.
Yeah. So I will start actually by telling you about this, the geometric aspect of this theory and how you can make sense of the initial value problem in a way that doesn't require arbitrary choice. Okay, so that's going to be the theory of the initial value prime in general relativity. And as you can see, this is a theory that's already 70 years old, a very fundamental theory, but that came much later than general relativity itself. So in a sense, 1952 to 1993, it's a little bit the prehistory of the subject, even though there were some interesting results. Really, the first landmark came 30 years ago. We're celebrating the anniversary this year in the stability of Minkowski spacetime. So this is a monumental work, more than 500 pages of very deep quantitative estimates, and more than that, it's sort of open completely a research field. So it's really most of what we do today is based, at least in the beginning, on this work on stability of Minkowski. And what is it? It's the simplest problem you can think in dynamics. Take the trivial solution of general relativity, Minkowski spacetime, perturb it a little, and see what happens. And see that in fact the perturbation sort of gets dispersed, fades away, and you will come back to Minkowski spacetime if you wait for a very long time.
Perturb, you mean perturb on some initial surface?
Indeed, yeah, I'm going to come back to this, but yes, that's exactly what it is. Yeah, indeed, Shelley, yeah. So that's for small perturbations. So I'm going to talk briefly about that. And then if you start to have large perturbations, it turns out you can form black holes. So I will explain what black holes are and a little bit about that story. So the point is that black holes, in principle, they don't exist ex nihilo, they are formed dynamically. So, so the physical process in real life, sort of, it's a star that collapses. It's a star and it sort of becomes a black hole. So I will say a word about this, and then I will tell you about something that's much more recent. It is the question of the stability of these black holes. So you ask, black holes form. So then, what do they look like? And for that, you have to distinguish between two regions, which are the exterior and the interior. I'm going to come back to that, but roughly speaking, the exterior is where we are, and the interior is the point of no return. So you know that light cannot escape black holes. The interior is a region where, that's it, you can't escape anymore. And as it turns out, these two regions are very different. So there's been a lot of attention in the mathematical literature about the stability of the exterior in the last 15 years. In the interior, which is a subject that's very dear to my heart, as those of you who know me, they know this. This is a story that's being written. Okay, so it's not something in which we know that much. Okay, there are some results, but not everything is known. But I think it's a very exciting direction for the next decade, and I think this will be one of the major directions the field is going to take in the next year. At least that's my personal belief. Okay, so without further ado, let me start. So I want to start with a sort of gentle introduction. So the first thing is that we model space-time as a single entity. So I did this to 1905 because I want to date this to, in fact, special relativity, okay, even before general relativity. And the idea is that space and time are embedded in the same object called a Lorentzian metric. And what it is, you can think of it as a sort of matrix with 3 positive eigenvalues and 1 negative eigenvalue for the dimension of time. So for instance, you can think the matrix -1, 1, 1, okay, so which corresponds to this. Then this is an example of a space-time, and that's actually what's called the Minkowski metric. It's probably the most important solution in general relativity. So how does it work to have a space-time? Well, the idea is simple. So you have a diagram where time is a vertical direction, and then the horizontal direction you put space. And the rule is that if you have a curve that goes more or less that's more or less vertical, so either fully vertical or with an angle that's less than 45 degrees, then you say this curve is time-like. And what does it mean? Well, if the curve is a geodesic, meaning if it has no acceleration, it means that it's a trajectory of an observer. Okay, so for example, right now I'm on my chair in my office. I remain in the same space in space, right? But I just aging, okay, in time, and so I would be that trajectory. Okay, so I'm at rest and just move forward in time. And here it's an observer that moves, but at uniform speed. That will also be a time-like observer. So, I mean, a time-like curve which models, the path of an observer. Then there is a limit case, which is exactly 45 degrees, so between the horizontal and the vertical, and that's the null case, and that's a trajectory of light. So that's the path of a photon. And why is it at 45 degrees? Well, because the way I think about this is that I take speed of light to be 1, okay, normalized. So if I move 1 unit of space in that direction, I have to move 1 unit of time in that direction if I am at the speed of light.
Good question.
Did I crash something?
Question.
Yeah, Shelley.
I know it's probably sort of traditional, but really why, when you talked about these time-like curves, you said it's a time-like observer rather than just a time-like object.
I misspoke. So it's a time-like curve that models the path of an observer. Yeah, I misspoke, sorry.
Why observer rather than just object?
Well, I mean, I don't know what happened with my screen though. Something strange, very strange happened. It's more of a sort of traditional expression. You're right. I mean, it is an object. It's an object that doesn't go at the speed of light, and that's it. You're right in that sense. I think we emphasize the word observer because then we want to speak about proper time. So we sort of put artificially a conscience to this object by calling it an observer, but in reality, it's completely unnecessary. I agree with you. Can people still hear me?
Yeah, we can still hear you and we can still see you.
But you can't see my
your other computer crashed probably.
I think it's because I don't have. Okay, let me. I think I'm not connected to the internet for whatever reason. Give me just 1 second. I don't know why it stopped being on the internet, but okay, so let's do this. Sorry, 1 second. I'm going to come back on the Zoom. Okay, that seems good. Okay, I think I'm back. Sorry for that. Noise technology. Okay, now you can see the screen?
Yes.
Okay. So this is for the more or less vertical curves, are like observers or objects, massive objects. The massless ones, the photon, they go at 45 degrees. And if you wonder what are the sort of vaguely horizontal ones, those more models of the geodesics of the shortest length between two points. So that's more how you should think about them. Okay, so that's that's the Spacetime 101. Now let me talk about general relativity itself. So the postulate of general relativity is that spacetime obeys the Einstein equations. So the Einstein equations relate the curvature to the content of matter in presence. So the curvature is in fact only the average of curvature, so the trace, the Ricci tensor. And T is represent the energy, more precisely the stress energy of the matter field that you have. So two important remarks is that there is a case in vacuum, okay, and in vacuum there is a trivial solution which is a Minkowski metric, okay, and it's trivial because not only the average of curvature is 0, but the whole curvature is 0, in fact, okay. So that's why it's a trivial solution, but you can have solutions which are non-trivial, so they have 0 average spacetime curvature, but they still have some curvature, right? Some Riemann curvature. And in particular, it's important to know that such solutions exist in vacuum. So black holes, for example, can exist in vacuum. Okay, so we have an equation, and as analysts, we like to understand what's behind this equation, what is its nature. And if you think about it for long enough, you would see that the principal symbol of this Ricci term is in fact a wave operator. So it's a box operator that depends on the geometry. So you see it's a box that depends on G, and it's applied to the coefficients of G. And in vacuum, this would be 0. So you should think about this, okay, in quotation marks, as something like minus dt squared plus dx squared plus dy squared plus dz squared, and then a bunch of horrible nonlinearities, okay? So because there is an intrinsic wave nature to the Einstein equation, that means that any perturbation will propagate at the speed of light. And this wave nature is what's at the origin of the famous gravitational waves that were recently observed by the LIGO interferometers. And this is actually amusingly something that was predicted by Einstein himself, even though he wasn't so sure because there was a lot of back and forth on this. But for some reason, even though sort of in theory it made a lot of sense, their existence was very controversial until they were finally observed in 2015. So you can see here in this picture that if you have a perturbation, here you have two neutron stars, they create some ripples, and those ripples sort of propagate. So that's sort of the intuitive picture you should have for gravitational waves. And so it means that sort of anything that happens in dynamical general relativity is about these gravitational waves that propagate. So now that we have some intuitive picture, I think it's important to give credit to Shortship for in fact giving the basis of her field, which is how to formulate the initial value problem. So this is something she achieved in her PhD thesis, which is quite remarkable. I mean, you found a research field in your PhD thesis. That doesn't happen all the time. In 1952. And the idea was as follows. So take a snapshot of space-time at time equals 0. Okay. So place some initial data there. Okay, maybe you need to choose some coordinates for that and so, but let's disregard this issue. So you place some data, okay, and then so these are data that would be consistent with the wave equation, because for wave equation you need to prescribe an amplitude and a time derivative, and then solve for the Einstein equation, okay, until you get what's called a maximal solution. Okay, so maximal space-time. So it's a maximal globally hyperbolic development. That's the official name. If you never heard this term, don't worry, just think that there is a way to solve and obtain a maximal solution. Okay, so this was a revolution. And this is what allows you to speak of the evolution of data in a completely geometric way, and in a way that does not require any choice. In particular, does not require to foliate a space-time by time slices. You don't really need to, following up on the question of Shelley, you don't really need to choose a time for this to be defined. Okay, even though you need to choose an initial surface, that's true, but you don't need to choose what time is to make sense of this.
How did Shortship, how did she, let's say, address the issue of the whole problem?
What do you exactly mean by this? You mean how did she prove it?
Oh, just how did she speak about it for a broader audience who might be puzzled, like Einstein was in 1917 or 18, about the whole problem? What did she say to address it?
So her idea, so it was all based on the clever choice of coordinates in a way. I don't really think that sort of, I think she understood, and that's something else.
Maxime, I think Shelley means whole, H-O-L-E, not W-H-O-L-E. So
That's
maybe
right.
Shelley, you want to say what that is?
I do mean H-O-L-E.
So the whole issue?
Right.
You mean the black hole issue?
No, not the black hole issue, but suppose you were naive, you're not sophisticated, and you're looking for a solution to given the initial data. Well, it's not, and you already have coordinates somehow. It's not, because of diffeomorphism and variance, there's not going to be a unique solution unless you take into account the equivalence.
Sure.
In other words, a different situation than with normal partial differential equation.
Yeah, absolutely, absolutely. I think she was well aware of the diffeomorphism invariance of the theory. I don't know if Einstein was. I know she talked to him, but I don't know if he understood sort of the real depth of that diffeomorphism invariance. I don't have sort of.
I think he did, because he worried about it for about 6 months or something like that. Michael, if he's around, would know better. He really worried about it a lot, but then I think he came to understand what the situation was. But he was he was very worried. I assume she was well aware. I'm just wondering how she expressed it in the paper.
So, I mean, in the paper, there is, I forgot exactly what's written, but I can look it up if you want. I think she
just shows some gauge condition.
She certainly introduced some gauge condition. So what she chooses as a gauge condition is that the coordinates propagate following a wave equation. But nonetheless, I think she was aware of the diffeomorphism invariant character of the theory, and she was aware that the notion of a maximal globally hyperbolic development was a gauge invariant notion. I think he also clarified a lot. So, okay, to be very fair, he also clarified a lot, after she spoke to Garrosh about these issues, because he was very aware of these geometry constructions. And I think that's also in the sort of like, she doesn't really say the word maximal globally hyperbolic development in the 1952 papers, if I have to be honest. It's only after the work with Garrosh that this notion has been completely clarified. And right now, so the paper to read is the one in 69, not the one in 52, I would say.
Let's see, that's interesting, because when I was a student, and I was worried then about the whole problem. I was confused too. And I remember my professor, it was Peter Bergman, telling me, Garrosh solved this completely.
I see. Yeah, I think that's quite. Yeah, I think that's quite true. So the sort of mathematical breakthrough, the sort of like piecing things together, having the right coordinate, the wave coordinates. I think this is the idea of Shokebura. But I think sort of, the prime was completely solved only after the second paper, in the sense of the geometric aspects. I think it's fair to say. Yeah, agreed. Okay, so now that I've spoken about the framework, let me tell you about sort of beginning of history, sort of having some hard estimates, because even though it's a PDE result it's a little bit more soft, what Shokebura has done. Here we're really talking about hard estimates in the stability of Minkowski. So remember that the Minkowski space is a trivial solution, so it's completely flat, okay? And so your naive question is, you have a perturbation of Minkowski, and what happens to it? And the framework to address this is a framework of the initial data of Shokebura. So take some data which is close to Minkowski, meaning which is very close to being flat. It has very small curvature, as encoded in some Sobolev type norm that we know and love and that you would use in PDEs. Okay, then see what happens. Follow the evolution, and when you do that, and it's a very deep result. Christou and Kleinerman have proven that the solution is geodesically complete, so that means the geodesic continue forever, and more importantly, that the spacetime reverts back to Minkowski if you wait for long enough. Otherwise said, the curvature that was small in the beginning ends up dispersing and tends to zero as time tends to infinity. So this is a very important result, and not such an obvious one, because you could have thought that, for example, you could create a black hole with a very small perturbation of Minkowski, because after all, black holes can have arbitrarily small mass. So even at the time, it really clarified things, even I think in the physics literature. So it's a very, very important result on which a lot of nonlinear techniques are now based. So
the four-dimensional curvature just determined entirely by on a slice, determined entirely by G0 and its derivative?
It's time, yeah, G0 and its time derivative, yeah, that's enough. I mean, so it's a Lie derivative. Okay, I swept something under the carpet. It's a Lie derivative. It's a second fundamental form in reality, but yes, that's sufficient to determine everything initially. I mean, of course, it's G0 and some spatial derivative, right? They are, you're also allowed to, so since you prescribe G0, you can also take spatial derivative at G0. But yeah, playing, with the equation, that's enough. Playing with Farabici of G equals 0, that's enough to prescribe all curvature components. Yes. So, so that's what happens when you have a small perturbation. What happens when you have a large perturbation? Well, the naive expectation when you have a large perturbation is that you can form a black hole, but surprisingly, it's a very fundamental problem. This was only solved in 2007. So, and the sort of 2007 result, I mean, I don't want to say it's the end of the story completely, but it's really a very satisfactory result in which you can say that the question of dynamical formation of black holes is essentially settled. And the artisan of that is Christodoulou, so I'm going to say that in a second. But before that, I want to first sort of give you an intuitive picture of what a black hole is. So I think I could show you a space-time diagram, but I think for first exposure, it's best to first see a snapshot of a black hole, so constant time. So this is just space, okay? So this is just space, okay? And a black hole is as follows. So it has an exterior and an interior. So this is the exterior. Let's say this is us. This is my office in here, okay? So we are safely in the exterior of the black hole, and we look in the sky, and we see this sort of very dark blob, you know, in the sky. And we can't see through it, right? It's completely black, okay? And this is a black hole interior. This is what we see. Okay, so we would see it as some form of black sphere, let's say, or deformed sphere from the outside. And once you fall into that, so you would fall into it, you would cross, you know, the event horizon of the black hole, and then once you get into this orange region, you can't go out. That's it. Okay, so in fact, gravity is so strong there that light cannot go out, and that's why, you know, the black hole appears to be black from the outside. So there is this terminology that there is a region, the exterior region, this is where nothing happens, quote unquote, okay? And the interior region, that's sort of the point of no return. So that's for a snapshot, okay? Now let me show you a space-time diagram and explain how that connects with the Lorentzian. Go ahead, Shelley.
Could you go back to the picture? So what's the meaning of the lighter green on the outside?
It doesn't really have a meaning. It's just to say, okay, the only thing is that it's asymptotically flat. So, so sort of here, this becomes, when r tends to infinity, this becomes flatter and flatter. So that's sort of the only thing. But there's not really a very deep meaning beyond that.
There's no sharp boundary between the two.
Yeah, there's no sharp boundary. That's right. Yeah. Sorry that it wasn't clear. I should maybe have used the same color. Thanks. So, so how do we connect this notion of a black hole with our knowledge of Lorentzian geometry? So, okay, very intuitively, it's as follows. So we have a space-time, and we can define infinity. So there are rigorous ways to do this, but let's stay at the naive level. Let's just take a function that's some distance to the origin. Let's call it r, and let's take r equals infinity, very naively. Okay, and then let's talk about the past of infinity. So the path of infinity, this is a set of points at which I can send a ray of light to infinity. So that's a bit jargony, but it's a very intuitive thing. If I have a flashlight, I don't have a flashlight in my office, but okay, I'm going to pretend that I have. Okay, so I have a flashlight. Okay, I turn it on, the photon goes away from me, and it's going to go, if it's unobstructed, it's going to go very, very far, right? And if I wait for infinite time, it's going to reach infinity. Okay, so I am in the path of infinity in particular. And you may think that you can always send a photon to infinity, but what's crazy about black holes is that there are some regions of space-time where you cannot send light to infinity, and that's exactly what the black hole interior is. So let me explain that with a space-time diagram. So if you're here, remember that light goes at 45 degrees. So I'm here, I can send a ray of light here. And here what I've done is that this infinity, I've drawn it at finite distance, okay, just to make the drawing a little bit more legible. So this is infinity, what I drew in green, okay? So you see, I can send a ray of light here to infinity. I can also send a ray of light towards a black hole if I want, that's fine. So I have two choices, right? I can send a ray of light sort of outward, you know, the yellow one, which is infinity. I can send a ray of light inward, you know, towards a black hole, but I can reach infinity nonetheless. So that means that here I am in the exterior of the black hole, okay? If I am in the gray region, however, it's a different story because light also goes forward. So I have still like two rays of light, the blue and the yellow. But as you can see, both rays of light are constrained to remain in the dark gray region. and in particular cannot reach infinity either here or here. Okay, you have two infinities here. Okay, none of them can be reached by once you are inside the gray region, and that's why the gray region is a black hole interior. Okay, and so that boundary that is here, now I'm sort of lacking colors, that boundary that is here, and also this one, is called the event horizon. That's a boundary between the interior and the exterior. Okay, so that's
say before about the blue line going from the red mark in the exterior.
so what's the question, Sherry?
What did you say earlier about the blue curve emanating from the red mark in the exterior?
Right, so I'm just saying that I send light inwards towards a black hole. I can do that. This is a ray of light that this one does not reach infinity, right? This one does not reach infinity, right? It's a little bit as if, you know, you have a sphere, okay? And you're in the boundary of a sphere. You can send a ray of light towards the outside of the sphere or towards the inside of the sphere. This one, the blue one, is towards the inside. But what matters is that I can also send the yellow one that's towards the outside, and that's going to reach infinity. Does that make sense?
Yeah, thank you.
Yeah, thanks. Okay, so that's for the black hole, okay? And now to the result of Christodoulou. So the result of Christodoulou is a mathematical realization of a diabolical machine.
I mean, about the history, I mean, Christodoulou has important results, obviously. That's why you're telling us about them. But what about the results of Hawking and Penrose?
Yes, I could have spoken about this. So the result of Hawking and Penrose was of historical importance. You're right. I mean, I told you this was a selective history. You know, this. I'm not saying this is less important, but I just chose to not speak about it. I can tell you why this result is important of Hawking and Penrose. So what they did is that they said that if there is a trap surface, then there is geodesic incompleteness. So it's an incompleteness theorem, and it's sort of funny because this has huge historical importance because it is what convinced people that black holes were not crazy mathematical artifacts. Because the point is that if you perturb a black hole, you know, based on the Hawking, so now I'm digressing. Okay, I'm not talking about Christodoulou, but so if you have a black hole and you perturb it a little bit, okay, so black hole says Shortship, okay, Shortship, everyone said at the time, you know, this is a mathematical artifact, this is not real, you know, it's a crazy solution, blah blah blah. Okay, perturb a little bit Shortship, okay, you still have a trap surface that's almost obvious, okay, because trap surface is an open condition, so you still have a trap surface. And you still have geodesic incompleteness. So it means that sort of your black hole does not disappear because you perturb it. So sort of the Hawking and Penrose, you know, incompleteness result were sort of the precursors of black hole stability, if you want. It means that if you perturb Shortship, you know, the problem doesn't go away. And so this is what convinced people on the theoretical side that black holes were a thing, even way before they were observed. And so that changed the future of the field forever, in a sense. It has a different flavor than stability of Minkowski, and why I didn't talk about it is because it's a soft argument, essentially. So it's an argument that it's very beautiful, it's very geometric, but it doesn't require you to sort of understand the dynamics very precisely. It's almost a contradiction argument, in fact. So that's why I sort of didn't talk about it. But you're right that he had historical importance, and in fact, Penrose got the Nobel Prize for that reason, and it's in my opinion fully deserved. Even though the Nobel Committee called it a singularity theorem, misunderstanding probably a lot of things about what the theorem proves and what it doesn't, but that's another story. I can tell you over lunch if you want. Okay, so now let me talk about Christodoulou's result. So as I said, Christodoulou's theorem. So first of all, that was his PhD problem. Actually, I'm using it. So that's the PhD problem that Wheeler gave him, and sadly, Wheeler did not live long enough to see Christodoulou solve his PhD problem. But you know, nonetheless, you shouldn't lose hope. So probably how long? Christodoulou did the PhD probably the 80s. So this must be 40 years later. But it's a very beautiful, very beautiful result. So it's a bit of the mathematical realization of a diabolical process in which you concentrate gravitational waves. So what Christopher does, let me tell you sort of in short. So this is your data, okay? And he puts a pulse of gravitational waves. So it sort of like focuses gravitational wave like crazy in vacuum. So there's no matter whatsoever. And that will create a trap surface, which will then end up in a black hole. So black holes can form in vacuum, and they form out of concentration of energy, if you want, of energy, and that can happen in vacuum, or that can happen with matter also. But here, sort of, this gives a very compelling mechanism for the formation of black holes, and this is sort of beautiful because the previous result of Christodoulou and Kleinemann was about waves of small amplitude, and now this is a large amplitude result. So of course, it's not anything large amplitude. I'm not saying that any large data forms a black hole, but it's something specific. It's a short pulse that's a very large, amount of energy that will then create a black hole. So let me just say a word about the word trap surface, because do you still see the screen?
Maxime,
Yeah.
can I ask a question before you go on?
Yeah, that's a good moment to ask, because actually the screen sharing just dropped. So yeah, go ahead, Eric.
Okay. So I understand that Christodoulou, he created this. He used this short burst of gravitational waves to create a trap surface, right?
Mm-hmm.
But the motivation here that you started, with this whole thing are the dynamical formation of black holes, right? And so from an observational perspective, like what we normally see from how black holes form is that you have a lot of dust around, and then the dust collects together until eventually it collapses into a star, which then eventually collapses into a black hole, which is not quite this gravitational burst that Christodoulou has done. And I asked Martin, about this, and he said, like, okay, well, it's just the PDEs are much solver if you use gravitational radiation than if you were to do the other way. But I'm just curious, like, are people trying to solve this other problem? Like, so suppose you start with initial data that has a little bit of dust in the middle, nothing that's formed the trap surface in the middle yet, right? So it's just dust. But then can you solve it and evolve it into a way where eventually you get a trap surface? I mean, are people looking into this?
Yeah, no, that's a very interesting problem. And actually, Christodoulou has resolved this problem in spherical symmetry.
Yeah, in the spherical symmetry, I know he's done it, but yes, outside of spherical symmetry.
Outside spherical symmetry, yeah, I mean, well, note that it doesn't have a trap surface, the data that Christodoulou has here, right? It doesn't have a
here Christodoulou doesn't start with a trap surface, but his way of getting a trap surface is not as physically realistic as I imagine black holes forming.
That's true. Yeah, I mean, I don't know if there are some people working on it, but this is certainly a very interesting thing to look at. So how black holes form, sort of like by sort of condensation of matter. Yeah, that's certainly a very interesting thing to look at. That's why I say it's a diabolical machine, because sort of you imagine you have a big laser and you sort of try to make a hole in space-time. Sort of this is not how black holes form. Indeed, that's true. So that's true that this is a very interesting direction to explore. I agree with you.
Okay, cool. Thank you.
Thanks for the question. Okay, so can you still? Oh yeah, you can still see my screen. Okay, so now that we see that black holes form, we want to describe how black holes look like.
Maxime, could you say again exactly the way how the Christodoulou result is better than the Hawking or Penrose result?
So Penrose result, okay, it's completely different. So Penrose and Hawking, okay, tell you that Penrose and Hawking is that if you have a trap surface already, okay, then you have geodesic incompleteness. You have one geodesic that does not terminate. Remember stability of Minkowski, all geodesics are complete. So that already means that you don't have, you can't destroy a black hole. You can't make a black hole Minkowski-like just by perturbing it. That's sort of what it says. But it has a huge assumption that you need already a trap surface. And by now we know, in fact, and they didn't know this at the time, but now we know that if you have a trap surface, it's very easy to show that the black hole is not empty, that you have a black hole. So it was of historical significance, but it doesn't tell you how trap surfaces form. So maybe I should have said what a trap surface is. So a trap surface, so think of a sphere, okay? it's a surface. So normally, if you are on a sphere, you can send light inside, and let me make it in blue for consistency. So you can send light inside, and you can send light outside. Okay, so that's a normal case. Okay, so that's a normal. Okay, if the sphere is trapped, sphere on another surface, then you can still send light inside, no problem. But whenever you try to send light outside, for some reason, it goes back in. So that's why it's called trapped. Okay. And what Penrose and Hawking have shown that if you have such a trapped surface, and then at least one geodesic that does not terminate, that terminates in finite time. So if you're an observer, you're going to exit the space-time in finite time, finite proper time. Okay, that's why also we use the word observer, because objects don't have clocks, but observers can measure time. So that sort of was a Penrose-Hawking result. Whereas Chrysalis tells you that even if you start with data that does not have a trapped surface, you can form it out of focusing by just taking a big laser and sending a huge pulse, and then you create a trapped surface that then evolves into a black hole. So you can, if you want, even combine Chrysalis' result and Penrose-Hawking to say that from the data of Penrose, you have geodesic incompleteness. If you want, you can combine them. But in a sense, you can't compare those results. I mean, neither of them supersede the other. But in a sense, qualitatively, the result of Chrysalis is much stronger in a sense, in that it tells you that you can create trapped surfaces out of just focusing. Whereas the Penrose-Hawking tells you something that, if we had understood the story in the right order, we would have said, okay, if there's a trapped surface, there's a black hole. If there's a black hole, then there's something to understand. There might be geodesic incompleteness, So it's more the Penrose-Hawking is more of historical significance than anything else. You can't really use it for practical purposes as opposed to the result. Did I answer the question?
Yeah. So should Krista Dulu have gotten the Nobel Prize?
Yeah, probably. Yeah, probably. I think so. Yeah. I mean, it's not his only contribution. It's really made, when you create a whole field by yourself, I think you probably deserve a Nobel Prize, right? But okay, Penrose has also made, the thing is that, I love Penrose's contribution, and the incompleteness theorem is one that's very important, but I think he's deserved the Nobel Prize for other reasons, for other works that he has that are equally impressive. I don't really understand why they restrict the Nobel Prize to just the geodesic incompleteness theorem. I think it's because of the historical significance. I think that's the reason. But in reality, he deserved it for many more things, I think. Okay. So let me now talk about how this black hole look like. So the first model of a black hole you can think of is the Shortship black hole. So there's the story of the Shortship black hole is a bit peculiar. It was only found 2 or 3 months after Einstein published his paper on general relativity by Carl Schwarzschild, which I think was then on the battlefront in World War I, actually. So he sent this note to Einstein. And I think by the time Einstein received them, or a few months later, at least, he died during World War I, I think, of disease. So it's a very tragic story and peculiar one. The Shortship solution represents a black hole that does not rotate, that is stationary, doesn't depend on time. So by that, I mean that there is no time. You see, there's no t. There's a dt squared, but the coefficient don't depend on time. And it has a mass parameter that is strictly positive. And you can observe that if the radius is equal to 2m, then there is something funny going on in this coefficient. So you see, if I equals 2m, then you have, this is 0 to the -1, so this is infinity. And this created a lot of confusion at the time. People said there is a very bad singularity, the solution is ill-defined. It created a lot of solutions. There's one person who sort of understood, the confusion before anyone else. It's a sort of obscure Belgian priest in the 1930s called Georges Lemaitre. He was not a physicist, he was not in the academic communities, but he wrote a bunch of papers that were essentially ignored until much, much, much later, and that were rediscovered, in fact, by Penrose in the 60s. And he had understood that, in fact, this I equals 2m is in fact an event horizon, it's regular. So how do you see this? Well, you just have to change coordinates. So there is a standard way now to write this coordinate change. I mean, you can call this a Lemaitre coordinate change. Eddington and Finkelstein also have found this. And you can then observe that if I equals to m, the only issue that this thing is 0, but there's no infinity anymore. And so once you realize that, okay, your view of the world gets expanded all of a sudden, and you realize that I equals to m is the event horizon of a black hole. So then you can draw a space-time picture. And really, the very important thing is that when you cross the event horizon of a black hole, nothing happens to you. This is not a singularity. You don't get crushed by anything. I mean, of course, you can feel some tidal deformations that you would feel on the outside anyway, but there's nothing specific from the point of view of an observer when crossing the event horizon. Of course, there's some significance globally because that's the boundary of the black hole region, sure. But from the point of view of the observer, you won't realize when you cross the event horizon. You really won't realize. But shortly after, after you cross, the event horizon, so you cross the event horizon here, you will end up when I equals 0 at a singularity. And you can see very well that when I equals 0, that coefficient becomes very singular, right? And in fact, so the scenario will not be very pleasant for the observer. He or she will be spaghettified. So the tidal deformation between your feet and your leg, will elongate you infinitely, experience infinite curvature, but also get spaghettified. So that's what happens if you fall into a Shortship black hole. So the Shortship black hole is a lovely model, but it's not very realistic because it does not rotate. And nowadays we know that, well, as Eric said, black holes are formed of collapsed stars, and stars have momentum. And so we need a black hole that has a momentum as well. And that took much longer, almost 50 years before it was discovered, and it's now called the Kerr solution. There's a funny story about the Kerr solution that I'm happy to tell you at lunch, but let me not say no more stories for the day, I guess. So it's
when you say momentum, you mean angular momentum?
I mean angular momentum. Thanks, Shelley. Yes, I mean angular momentum indeed. So there is an extra term, that involves A. So you have this bunch of A's everywhere. So it's not a spherical anymore. It's a sort of elongated sphere, kind of ovoid shape. Okay. So it has its A's everywhere, and A is the angular momentum. So A equals 0 corresponds to Schwarzschild. And like Schwarzschild, it has an event horizon, which is R equals a constant. Okay, it's not 2m, but some constant depending on m and a. And if R is greater than this is the exterior. If R is less than this is the interior. And again, if you cross the event horizon, nothing funny happens to you. So this black hole, you have this stationary solution, and the natural question, in line with stability of Minkowski, it's a question of perturbation. So is this black hole stable to perturbations? And it's a very important question because if something is unstable to perturbations, then it doesn't have any astrophysical relevance. That's something very important to note. It's like the unstable equilibrium of the pendulum, right? As any of you observe this, right? So things that are unstable sort of have much less relevance to astrophysics, of course. So it's a very important question. And of course, this will be phrased in the framework of the initial value problem. So take data that is very close to Kerr in the suitable norms and see what you get. And the conjecture is that Kerr is in fact stable, but in the following modified sense, it's not that if you take a Kerr black hole, you converge to the same Kerr black hole, you converge to a different Kerr black hole, okay, as time tends to infinity. But the difference in angular momentum and mass compared to the old and the new is very small, okay? I mean, the reason is that because when you have a perturbation, the perturbation carries a little bit of mass, and that mass is accumulated towards a black hole. That mass and the momentum is accumulated towards a black hole and does not disperse, as opposed to Minkowski, where everything disperses. Okay, so that's sort of the difference with Minkowski. That's why it's a much harder problem with stability of Minkowski. And so this problem, so I said 2022 plus because it's a problem that's reaching an end very soon. So let me tell you sort of what's known. So what's known is that if you have very slow rotation, then this is known, and there was some result of Kleinemann-Schefter and Georgi Kleinemann-Schefter that sort of settled the last details of this question. I want to also emphasize that this is a problem that was revived by Penrose and Rynewski in 2008, and there was many contributing authors in the meantime. And if you don't have small angular momentum, well, all the details haven't been written, but there is at least a skeleton. So there is a way to interpolate between all these works to sort of have a roadmap. And we have some indication on how it should work and why it's probably going to work. Okay, so not all the details are written, and maybe need to wait a little bit longer before having all the details written. But essentially, this is a problem that on the conceptual level is extremely well understood. And the conclusion is that yes, the exterior of the Kerr black hole, and exterior is an important word, is stable. So now I want to talk about the interior, and the interior is a completely different story. So the interior, in my opinion, it's perhaps the most interesting region. There's also the ones where the mathematical phenomena are perhaps more complicated, and the story is not as clean as in the other topics because it's a chapter that's being written. Okay, so you will forgive me if sort of some of the things I don't know. Ask me again in 10 years, maybe I will know more. But I want to sort of tell you a little bit about the various problems. Okay, so let me skip because been already many. I'm already running a bit late, so let me sort of skip the summary of what I said earlier, and let me sort of emphasize that the question is what happens once you cross the event horizon when you fall into the interior of the black hole. And your naive expectation may be that you will have a singularity because that's what you have for the Shortship black hole. And in fact, if you ask a random physicist, and I really mean a random, sort of like you don't specialize in people that are doing black holes, they would probably tell you that that's what they expect, some form of singularity. Okay, and this is not wrong, by the way. So you may expect some form of singularity based on this. Okay. So this is at the heart of another conjecture in the field, which is one of the biggest open problems, which is called the strong-cosmic censorship conjecture, and I want to take a minute to explain. So this is at the heart of the following question: how can we make sense of the fact that general relativity is a deterministic theory? So what do I mean by deterministic? I mean that in the sense of Laplacian determinism. I mean that, for example, Newtonian mechanics is deterministic in that if you throw a stone in the air, then the motion of the stone will be perfectly determined by the knowledge of the initial position and velocity through the Newton equations. So in that sense, classical mechanics is deterministic. So in general relativity, it's much harder to make sense of that question because of the geometric nature, but the proposal of strong cosmic censorship by Penrose actually answers that question. And so what Penrose proposed is that prescribed data, time equals 0. So this is using the initial value problem formulation. Prescribed data, create your maximal solution. You know that you can do that by Shekebura. And then Penrose wants to say that this solution should be inextendable. So, so you're not allowed to extend. So this kind of extension is not allowed. Why does this make sense? I mean, you can propose other alternative if you want, but I can tell you at least why this one makes sense. So because the solution is already the maximal solution you can get from your initial data, the stuff in yellow. So if you were to extend that, this would be not determined by the data. So in particular, not determined by the Einstein equations. And you would need another theory to supplement the Einstein equations, another unknown speculative theory. So that means that there is more to general relativity than the Einstein equations, which is not very appealing. So
that theory could still be deterministic, no?
Well, not so much in that sense. Well, yes, if you had something else, but at least the current understanding of general relativity of using the Einstein equations would not be deterministic in that sense. It would be deterministic once you add something else that that you could make it deterministic by adding something else. Sure, in that sense, yes. So, from that perspective, let's come back to the Shortship singularity. Remember that Shortship singularity, there's a spaghettification that happens when I equals 0. And this is actually an interesting thing for strong cosmic censorship, because once you have a singularity, you precisely can't extend through the singularity, right? Because if not, you will have a singularity in the middle, and that's not allowed, by the rules of extension. So this is this paradox, and this is maybe, if there's only one takeaway of the talk, that should be this one, that, okay, singularities perhaps are not very nice for the observer that fall into the black hole, but from the point of view of the theory, singularities are excellent. This is what prevents you from extending and therefore restoring determinism. So that's something that's good to keep in mind. Except that, so for Shortship, everything is well, but Shortship doesn't rotate, so you may want to look at Kerr. And in Kerr, you have the following disaster that the interior terminates in a Cauchy horizon, which is perfectly smooth, okay, not singular, as opposed to Shortship, okay. And because it is smooth, then in particular you can extend it. So that's very bad news because, and that's also why you cannot really rely on stationary black holes to understand the whole story, because that means that if you think of Kerr as your model of a rotating black hole, then this one violates determinism. So it's too naive to ask that all data respect determinism. But in fact, Penrose was already aware of this, and he didn't say all data; he said generic data. Generic. That's an important word. And well, the Kerr metric is not generic, right? It's very special. It's stationary in particular. It has tons of symmetry, in particular time symmetry, right? And so the question, sort of crazy hope, if you think about it, is to say, if you look at perturbations of Kerr, so if you sort of go outside of if you take something generic, can you make it respect determinism? And the crazy fact is that the answer is essentially yes. So that's also why I want to emphasize that there's something very fundamental in dynamical general relativity is that you would completely miss if you look at stationary solutions. And that's one of them, for example. So you cannot think, you said that a black hole, all black holes you want to say because of the exterior become approximately stationary if you wait for long enough. True. But no black hole is exactly ever stationary. And this is a subtlety that Penrose understood before everyone else, actually. He wrote actually these exact words in a 1969 paper. And being exactly stationary is different from, converging to stationarity. That's some very important distinction. And for determinism and strong censorship, it's a very fundamental one.
This extension that you had in red there.
Yes.
Exactly what's required of it? What do you mean by an extension? What does it have to satisfy?
Nothing. Nothing. That's the point. This extension is arbitrary, so you can extend by anything you want. Anything you want. It doesn't need to satisfy anything. The only thing that it has to satisfy is some compatibility condition on the green line, but that's it. So that means because you can extend in any arbitrary way you want, that means that nothing makes sense, right? That means that sort of the question is what happens to observers when they go to the extension makes no sense because you can extend any arbitrary way and you have no way to discriminate between the extensions.
Don't you just demand that the extensions satisfy the Einstein equations except at the boundary?
But you can't do that because sort of you would need to sort of then prescribe additional data, and the way that causality works is that if you prescribe data, you will only be able to solve up to the boundary. So that's sort of the beauty of the Einstein equation. That sort of you can't solve like this essentially. You can't solve because this is a characteristic boundary. So you cannot really solve by putting data there. So you really have non-uniqueness. You cannot prescribe the Einstein equation because of causality. That's an instruction that you really cannot go around.
Can I ask a potentially not smart question? Is CHI plus defined as the kind of like infinity, but from the inside of the black hole? Like if you...
Yeah, so I wouldn't like to call it infinity, but if you want, it is the boundary of the maximal solution. So you have a maximal solution, okay? This is a solution given by data. And so, this is what is predicted by the initial data. And this is a boundary of that. So in a sense, you can call it infinity, but it's a compact region. So like R is let's say 1 here. So that's why sort of like it's infinity in the sense that it's some boundary of something, but it's not really infinity in the sense that sort of, in particular, the point that if you fall into the black hole, then you would encounter this boundary in finite time in particular. So that's why sort of like it's not really an infinity in that sense. Does that make sense?
Yeah, that clears it up. Thank you.
Thanks. Okay, so well, I still have quite a lot to tell you, but sort of let me maybe cut to the heart of it and conclude because I'm sort of running out of time. So the main mechanism that is behind this is a Blueshift instability. So I'm not going to tell you. So there's been some results, you know, some by other authors, some by myself. Let me not tell you about my results. Sort of, you can ask me later if you're interested, but let me sort of cut to the main point because I wanted to give a review talk. So the Blueshift instability, okay, it's hard to prove, but it's easy to explain. So this is a situation. Yeah, you have Alice who falls into a black hole, reaches the boundary of the black hole, as I just explained after Larry's question, in finite time. So tau of Alice, the time of Alice. So Alice will experience, you know, this extremity of the boundary, this CH plus, in finite time. And Bob stays outside the black hole, on the other hand, lives forever. Okay, so the geodesic of Bob here is infinity. Bob is on the exterior. Okay, and Bob sends a message to Alice every second as measured by Bob, right? But the point is that what's sent every second by Bob is not perceived as being every second by Alice, because you see here, Alice has finite time, whereas Bob has infinite time. And remember that it's relativity. Everything is relative. The clock's time is relative as well. So Bob sends a message every second, but Alice on her own clock receives it not every second. First, it's maybe every second, then it's every 0.5 second, then it's every 0.01 second, then every millisecond, then every nanosecond, femtosecond, etc., until the frequency, so if it's received more often, the frequency increases, until the frequency becomes infinite. Okay, so the frequency of Bob is always 1. Okay, the frequency of Alice becomes infinite when Alice reaches a Cauchy horizon. That means the frequency is shifted to the blue, and that's what's called a Blueshift instability. Okay, and this causes all sorts of things. This causes okay, let me sort of cut to the chase. This causes, you know, the Cauchy horizon to have a singularity, and that singularity restores determinism. That singularity is what makes strong cosmic censorship true. Okay, but the singularity is very different from what happens in the Shortship black hole. It's much weaker. So otherwise said, if you are experiencing this singularity, you would probably get burned by infinite energy, but you won't get spaghettified. Spaghettified is worse. So and then this creates all sort of things. So then you may ask how does the rest of the boundary looks like, and this is also a very important question that, you know, Penrose asked, and sort of I don't really have time to explain to you my result on this, but sort of let me get maybe to the final picture. Sort of in spherical symmetry, we understand that there's a Cauchy horizon with a weak singularity from the Blueshift instability, and then in turn this Blueshift instability causes the emergence of a breakdown, which then in turn creates a strong singularity, which is very similar to the singularity of Shortship, in which you have some form of spaghettification. Okay, but all of that being said, we have all indications, at least in spherical symmetry, that strong cosmic censorship is true. One of the very important open problems in the future will be to understand this outside spherical symmetry. And it involves many steps that feel free to ask me about. I mean, there are many open problems with various levels of difficulty. Some of them would be great for PhD students. Some of them are a little bit more advanced. Some of them are probably lifetime research programs. There's certainly a lot to do. And as I say, it's a chapter being written, and we need as many people as possible working on it. Thanks for your attention.